Chapter 2.1, we're going to be going over certain properties of graphs. So starting with the difference between increasing and decreasing functions. We say that a function is increasing if it's rising left to right. So that would look something like this, if it's rising left to right. That means if x2, so an x-coordinate is x2 is larger than x1, then f of x2 is larger than f of x1. And all that means is as the x values are increasing, the y values are also increasing. And for an individual point, we say that a function's increasing at a single point, x equals c, if that point lies on an interval where it is also increasing. And for decreasing functions, we say a function is decreasing if it's falling from left to right, so something like that, it's falling left to right, which means as the x values are getting larger, then the y values are actually getting smaller. And then we say that a function is decreasing at a point if the point lies on an interval where it is decreasing. All right, and then here are some examples. And for the first one here, for A, we can see that it is increasing at C, at point C, because that's where the interval where the graph is increasing, it's rising left to right. For graph B, we can see that it's decreasing at point C because the graph is falling left to right. And then for part C here, we can see that it's neither increasing nor decreasing at C because that interval right at that single point, it's not the function's not increasing or decreasing, which we'll see what that means in a little bit. And for D, we can see that it's decreasing at C because the function's falling left to right. And for E, we see that it's increasing at C because it's rising left to right. So notice that we're doing everything left to right because that's how, when the x values are getting larger, left to right. So that brings us to extreme points. And a relative extreme point, so just remember that we can use the word local, extreme point, relative and local mean the same thing. A relative extreme point or an extremum of a function is going to be a point where the graph changes from either increasing to decreasing or decreasing to increasing. And the two types of relative extrema that we're going to be going over here are relative maxima and relative minima. And just so you know, you'll see that we're using maximum and maxima. If it ends in um, that is a singular point. If it ends in a, that is multiple points. So um ending is singular, a ending is plural. So relative max, a relative maximum point is going to be a point where the graph changes from increasing to decreasing. So taking a look at this graph down here below, we have a relative max at this point, x equals a, because it changes from increasing and then goes down to decreasing. And now taking a look at a relative minimum point. A relative minimum point is going to be when the graph changes from decreasing to increasing. So this other graph, we can see that it's decreasing and then it switches to increasing, which means we have a relative minimum at x equals a. Okay, and then just kind of also a little note here, relative max and min, they cannot occur at endpoints of the graph. And the next thing is the absolute max and min. So before, what we had up here, extreme points, they don't have to actually be the highest and smallest point on the graph. It just has to be when the graph is changing from increasing to decreasing or vice versa. Now the absolute max and min, these will be the largest value and the smallest value on the graph. So the absolute maximum value is going to be the largest value, and when we say value we mean function value, which is the y value. So the absolute max is going to be the highest y value on the graph, and the absolute min is going to be the smallest y value on the graph. So taking a look at these examples, in the first one here for A, we can see that the highest point on the graph is up here. That means that is the absolute maximum, which means the absolute maximum is the y value of 5. It's always the y value. And then we can also see that the lowest point on the graph is right here at 4, 1. So the minimum value is the minimum value of 1. And then for the next one, for B, For B, we have the lowest point on the graph right here is 0, 2. That means the minimum value is the y-coordinate of 2. And since typically we would have arrows on the end, but since there's no filled-in circle, there is an implied arrow on the right-hand side. If there's an arrow, that means there's no maximum value because it keeps on going forever and ever and ever. And unlike relative max and min, absolute max and min can be the endpoints, which we saw here in example B. Now let's see this example. So when a drug is injected intramuscularly, the concentration of the drug in the blood has a time concentration curve shown below. Describe this graph using the terms that we just did on the previous couple pages. So we have our x-axis is in time in hours, and our y-axis is concentration in milligrams per 100 milliliters. So first, let's take a look at the extreme points. So notice that we have a relative maximum at t equals, it looks like it's about t equals 2, maybe a little bit past t equals 2. So maybe I'll just put approximately t equals 2, and then I'll label it in hours. And that is because the graph changes from increasing to decreasing at that point. And then also notice that we don't have a relative minimum value because it never changes from decreasing to increasing. And now taking a look at the absolute maximum, there's an absolute max at the t equals about 2 hour mark, and the absolute max is going to represent the highest concentration of drug in the blood. And I didn't put the y value because can't really tell what the y value is. A little bit more than 0.05 milligrams per 100 milliliters. And then for the absolute min, there is a absolute min right here at the origin. That's at t equals 0 hours, and that just is because there's no drug in the blood at that point yet because we didn't administer it yet. And for the next concept that we're going to be looking at is how the slope of a graph changes. So for this one, and once again, we're going to be looking left to right because that's when the x values are getting larger. It's pretty much always left to right. So for example, to kind of demonstrate how slopes change differently, we have these graphs down here. And we can see that both of these graphs down here, 1 and 2, they are both increasing, but you can tell that there's a difference in the way that they're increasing. They're increasing at a different rate. So graph 1, if we're looking at the interval from 1960 to 1990 for now, 1960 to 1990, you can see that for graph 1, it's steeper at 1990. So right here, it is steeper than when it is at 1960. And we can also see kind of in general that the slope increases from left to right for graph 1. So what we have up here, because this graph, what it actually represents, the x-axis says the U.S. gross federal debt per capita, and the y-axis is dollars per person. So it's representing the federal debt per capita in dollars per person. So if this was a newspaper, then we might read as the U.S. gross federal debt per capita rose at an increasing rate during the years 1960 to 1990 because the slope increased. So if we look at graph 2 over here on the right, it looks like the slope is decreasing from 1960 to 1990. So from here to here, it looks like the slope is slowly decreasing. So, excuse me. So we might say that for the newspaper, that the U.S. gross federal debt per capita rose at a decreasing rate during those years. So they're both increasing, but they're increasing at different rates. And that's where this next topic is going to cover. So we say that the slope is increasing if it's becoming steeper, just using terms that we're familiar with for now. And we say that the slope is decreasing if it's becoming less steep. So for example, we have these two graphs, and you can see that both of these graphs are decreasing, right? And we know that they're both decreasing because they're both falling left to right, but they are decreasing at different rates. And we can see by this one over here on the left, the slope is becoming more negative, so that means the slope is decreasing. And then the one on the right, the slope is becoming less negative, so that means the slope is actually increasing. So the graphs are both decreasing because they're falling left to right, but the slopes are changing differently. The one on the left, the slope is decreasing. The one on the right, the slope is increasing. And since obviously this terminology gets very confusing, talking about slope increasing, decreasing, we're going to be using the term concavity to discuss how the slope changes. So concavity tells us how the slope changes. So let's go ahead and get into it. So concavity, we're going to have two different types. We're going to have concave up and concave down. So we say that a function is concave up at a point if the tangent line lies below the curve at the point. So concave up, tangent line lies below the curve. And the way that you can kind of think about it for the most part is that the curve is opening upward because it's concave up, opening upward. So you can see that we have this example here, and here's the curve, and these tangent lines are below the curve, so that's how we know that it is concave up. And also you can kind of see how the graph, it looks something like this. You can see how it's kind of opening upward, meaning it's concave up. And what this means in terms of the slope, it means the slope is increasing from left to right. And you can see with the tangent line, we have the slope of this line, the slope of this line. As you move left to right, the slope is increasing with those tangent lines. Next one, we have concave down. We say a function's concave down if the tangent line lies above the curve at a point. And this means that the curve is opening downward, so concave down, the curve is opening downward. And we have this curve right here. It looks something like this. And we see that if we put a tangent line at some points, we can see that the tangent line is above the curve, meaning that it is concave down. And we can also see that these slopes of the tangent lines are decreasing, which means the slope is decreasing from left to right. So for concavity, we're going to have points where it changes concavity. It's going to go from being concave down to concave up, or vice versa. And the point where it changes concavity is called an inflection point. And we can see some examples here on this graph. We have three different little portions of the graph here. And for this first portion, we can see the graph is concave up, and then it switches to concave down. You can look at the tangent line for help. Tangent line is below, and then tangent line is above, meaning it goes from concave up to concave down. And then these points right here, these points are all inflection points where it changes concavity. Okay, let's take a look at this graph and use the terms that we just defined to describe the graph shown below. So starting with the relative max and min, you can see that there's a relative maximum point at x equals 3 with a y value of 5. So you can see these tangent lines at these relative max and min have a slope of 0 when it's changing from increasing to decreasing, or vice versa. And we can also see that we have a relative min here at x equals 5, and I guessed the y value. It looks like the y value is about 3.3-ish. And for the next thing, we take a look at absolute max and min. There is no absolute max or min here because the endpoints are, we can think of these as arrows on the end because there's no filled in circle or open circle. So it keeps on going forever and ever from negative infinity to infinity, so no absolute max or min. And the last thing is going to be what we just went over, is concavity. So starting with concave down, we can draw some tangent lines to help. If we draw a tangent line right about here, you can see that it is above the curve, meaning it's concave down. And you can just kind of tell by looking at it. from here to here, the curve is opening downward. So that means it's concave down over that interval. That's going to be the interval negative infinity to 4. Right, negative infinity to 4, using interval notation, it's concave down. And then once we get to this point at 4, it switches to concave up because it's opening upward. The tangent line is below the curve, and that's concave up from 4 to infinity. So at that point 4, we can see that it changes concavity, and that means there is an inflection point at x equals 4. Okay, and I'm also just going to throw in here, going back to the beginning where it was increasing and decreasing, just forgot to mention that. We can see that it's increasing from negative infinity up until 3, which was the relative max, and then it's decreasing from 3 to 5, and then it starts increasing again from 5 to infinity. So joining those intervals, we put a little u for union, so it's increasing from 5 to infinity also. Okay, just wanted to throw those in there. Okay, next thing is the intercepts, probably a little bit easier for this one. An intercept is going to be a point at which the curve crosses the y-axis or crosses the x-axis. If it crosses the y-axis, it's the y-intercept. If it crosses the x-axis, it is an x-intercept. And a function can have at most one y-intercept. If it has more than one y-intercept, it fails the vertical line test, and then it won't be a function. And a function can have any number of x-intercepts. It can have 0 x-intercepts, it can have 1, or it can have an infinite amount of x-intercepts. And also the x-coordinate for an x-intercept, we can call it a 0 or we can call it a root. So x-intercept, 0, and root essentially mean the same exact thing. So for example, if we have this graph, we have 3 x-intercepts crossing the x-axis, and we have the 1 y-intercept. Okay, so pretty simple for those ones, so we won't bother taking a look at another example. And for the next thing, we have undefined points. So some functions are not going to be defined for all values of x. Domains might not always be negative infinity to positive infinity. If we take a look at f of x is 1 over x, we can see that it is not defined when x equals 0 because we cannot divide by 0. 1 over 0 is undefined, so it's not defined there. And if we take a look at the graph right here, we can see that at x equals 0, there's actually a vertical asymptote, which I'll mention in a second. So there's a vertical asymptote right here, not defined at x equals 0. And if we have the function f of x is the square root of x, this is not defined for negative numbers because we can't take the square root of a negative and still get a real number. That would be imaginary numbers. So this is what this graph looks like over here. It looks like half of a parabola on its side. So that brings us to vertical asymptotes, which we just mentioned. A vertical asymptote is going to be when the curve approaches a vertical line as x approaches a certain number. So we can write this as a limit. It would be the limit of f of x as x approaches a is going to equal infinity, or it's going to equal negative infinity. If that's the case, that means there's a vertical asymptote at x equals whatever a is. And the most common type of vertical asymptote is going to be the x value that's going to result in dividing by 0. So if we have the function f of x equals 1 over x minus 3, that has a vertical asymptote at x equals 3, because if we plug in 3, it's 1 divided by 0, which is dividing by 0, meaning there's a vertical asymptote at x equals 3. And you can see these examples here. These dashed lines are the vertical asymptotes. You can see the function is either approaching infinity or negative infinity as the x values approach the x value of the vertical asymptote. And the next thing, we have horizontal and slant asymptotes. And for a horizontal or slant asymptote, what this means is that as the x value gets larger and larger, or more and more negative, then the function is going to be approaching either a line, a slanted line, or a horizontal asymptote. So what this means in terms of limits is the limit of f of x as x approaches negative infinity or positive infinity is going to approach a y value a. Graphically speaking, it looks a little bit more obvious. We have these dashed lines for a and b. Those are horizontal asymptotes. You can see as x approaches positive infinity, the function is approaching whatever y value that is. Similarly for b, as x approaches positive infinity, the function's approaching whatever y value that is. We say it's asymptotically approaching the value, meaning there's an asymptote there. And we can also have a slant asymptote, and that's just when the function's approaching a slanted line. So as x approaches positive infinity, you can see that this graph is approaching that slanted line, which would be a slant asymptote. Okay, so for the last little summary here, we have 6 essential categories that we're going to be using to describe the graph of a function. We'll continue this in the next few sections as well. We're going to be looking at the intervals where it's increasing or decreasing, which is going to help us determine the relative max and min. We're going to determine the absolute max and min value, so that's 2. If it just says maximum value, minimum value, that's absolute max and min. We're going to determine the values, the intervals, where it's concave up or concave down, and from that we'll find the inflection points also. We'll find the x-intercepts and the y-intercepts, undefined points, and asymptotes. So pretty much what we're going to be focusing on, the calculus portion here is going to be those first 3, increasing, decreasing, relative max, relative min, absolute max, absolute min, and concavity with inflection points. Okay, so we'll pick this up in the next section as well.